All right, welcome guys to our very last lesson, kind of a mini lesson today. It's really just one slide, and the reason is now we're jumping into section 11A, which is actually using the coordinate geometry and proofs. Hopefully you know how to lay out shapes to minimize the number of unknowns, and then we can use all the stuff from coordinate geometry, the midpoint formula, the distance formula, the slope formula, the fact that parallel slopes are the same and perpendicular slopes are opposite reciprocals, they multiply to -1, using all that stuff to prove things about shapes. Looking at the lecture right here, actually the homework right here, it's just kind of a lot of justifying, right? Look at this tiny stuff written out. These are all just kind of individual proofs. So this is broken out into 2 days. I think day 1 for homework, you're doing questions numbers 1 through 8, which is just like diagonals of parallelogram bisect each other. Yeah, that's pretty easy, right? Lay out the shape, name the coordinates, then use the distance formula, and then not distance formula, just use the how would you do that one? Diagonals of parallelogram bisect each other. Yeah, you just would draw on the diagonals and then prove that they have the same midpoint. Yes, that's right. Prove that the midpoints of connecting the two vertices of two opposite vertices, sets of vertices, have the same midpoint, and then you got to prove them. So anyways, you're just doing stuff like that. We're trying to think through and get it. Numbers 1 through 8 tonight for homework. And then tomorrow night for homework, you'll have numbers 9 through 13, which are just some start problems here, which are pretty tough. Just C-level problems tomorrow. But anyways, the reason why this is going to be a pretty quick one is that you may have seen this here. This whole section is just, hey, let's just look at one. Let's just give you one coordinate proof and then have you write your own. You're going to get it. You're going to be fine. So what I have here, this is a proof about proving the median of a trapezoid is parallel to its bases and half the length of the sum of the bases. Okay, so we have this here, and here's the proof. Because I think whenever I poll people and I ask, do you like this sort of more kind of paragraph proof, unstructured proofs, or do you like the 2-column proofs? A lot of you guys say you like the 2-column proofs. So because of this, all today's lecture is going to be that proving that exact theorem that we've talked about earlier in the year, that the median of a trapezoid is parallel to the bases of the trapezoid and has a length equal to half the sum of the lengths of the bases. So we're going to prove that, but we're going to do that in 2-column form because I think it does allow us to go a little bit more slowly, which is the right pace, right, for proofs, and to see the results clearly and really understand what we did rather than just looking at this thing and understanding what they did here. So this should be a better model for when you start with the homework, which is proofs number 1 through 8. So let's check it out. Let's jump into it. Okay, step 1 of proving something like this. Again, you don't have to write this. When you're writing proofs tonight, you don't have to write your givens and prove. This is what we here start with. This is what we're trying to prove. This helps keep the teacher organized here to be like, this is what we're going to need to get to. Our proof's not going to be done until I see this right here, that the median LD is parallel to a base, which PE is giving to us as a base, I guess, and then as another base. Although this looks like it must be written out incorrectly, because why would not? Let's keep going here. And so I need to see this, and I also need to see this, that LD, the median that's given to us, so that means that L must be a midpoint, and D must be a midpoint of the two sides of the trapezoid. Right, so the LD, the distance would be the sum of, get the distance MN, so probably use distance formula at some point, and distance OP, and then divide that by 2, and that should be the distance formula for LD. We should prove that LD is exactly that, like half the sum of the distances of the bases of the trapezoid. Okay, so step 1, right, to do this, what do we got to do first? Oh, that's right. Okay, so before we start writing the proof, we got to start laying out that figure. So I think you know what this should look like. Put a point here at the origin and mark that, I guess, we mark that O, I guess, and then lay OM on the x-axis that we have only one unknown for point M, and the y-coordinate would be 0. And then this top side here, when we draw in the other base, it's going to be parallel to the x-axis because it's parallel to side OM. And that's going to help us have only one unknown y-coordinate rather than 2 y-coordinates, because our y-coordinates would be the same. They'd be horizontal lines. Okay, so let's go ahead and draw that in. Draw it in if you haven't yet already. Oops, why didn't go out and do it nice and slowly here? So I like this kind of diagramming of this, that slowly we can draw it in. There we go. That's what I'm talking about. And we have this here. We have OMNP like this. Okay, so we have OP is the one on the x-axis, and MN is also a slope of 0, so they're parallel to each other. Okay, got it laid out there, and we know it's laid out like that because it's a trapezoid, which we'll get to in step 2. Okay, so point O, right? Lay out the diagram and label what you know of the coordinates, right? Before you start writing your proofs here. So point O is at 0, 0. Point M, do we know anything about those? No, we don't know anything about the slope of this, the slope triangle here, right? We don't know anything, so we need 2 unknowns there. So I'm going to label this as 2A and 2B. It might be a best practice just to label all your coordinates double what they need to be, because at some point you are going to find a midpoint of OM, because the median is going to go through the middle here and intersect the midpoint of OM and the midpoint of NP. So by having 2A and 2B here means the midpoint here won't be fractions. There'll be a whole number coefficient to it, okay? N here, do we know anything about that? Is it related to the 2A? And yeah, it's related to the 2A. It'll be greater than 2A, but we don't know. It's not like a parallelogram where we know this side length is going to be the same as up top here. So we'll give it another unknown, 2C, but we are going to know that the y coordinates would have to be the same. So we have 2b here and 2b here, okay? So that's sure what you get for laying it out. And then finally, p, what do we know about p? We don't know the x coordinate. Do we know the y coordinate? Yeah, it's 0. So we know, we might as well do d here because we haven't done a d variable yet. Okay, so we got 2d and 0. Okay, so let's jump into it. Let's get this proven here so we can drop in the old statements and reasons. And there we go, trapezoid OMNP, and LD is the median. So I drew an LD right there. Very good, I got LD. So that's kind of part of the figure, but kind of not because it's just a median, so it's not like a polygon or anything like that. So anyways, coordinates is marked, and there's properties of trapezoid. I haven't talked about that median next, so we probably might as well do that right now. Point L would be at AB, and I got that because that's the midpoint between points 2A and 0. Okay, so our average of the x coordinate would be A. Average of the b coordinates would be B. So L would be AB, and D would be C plus D, comma B. Okay, and because this would be 2C plus 2D divided by 2, which is just C over D. So here, see here, 2B plus 0 over 2 is just B. So see here, I get no fractions here when I figure out the coordinates of L and D, and then that makes distance formula a lot more elegant and easier to find out. Okay, so that's the midpoint formula right there. That's my reason. Okay, so let's get into it now. So I think first things first, it says you're proving that the median is parallel to the bases. We can do that now. We have coordinates assigned for all of at least 2 of the points on each line segment in this diagram. So let's maybe do this here. The slope of LD is 0. I can make that conclusion. Yes, totally. I can totally make that conclusion here. Look at this. Your delta y is 0. Y doesn't change. So y is b here, and y is b here, and b minus b is 0. So your delta y, change in y is 0. Doesn't matter what change in x is. It's not 0, so it's a positive number, I think. It just doesn't really matter what it is. But anyways, 0 over anything is just going to be 0. So slope of LD is 0, and that's the slope formula. Slope of OP is also 0 because right, our delta y is 0. The difference between 0 and 0 is 0. And slope of MN as well. Check it out here. MN. Make sure you laid it out correctly. Y coordinates don't change if it's parallel to the x-axis. So you have a whole bunch of slopes of 0. You get that from the slope formula. And what's that going to get you to next? What's that allow you to prove? Okay, that thing, we didn't really have a section on it, right? But you should know it, that if your slopes are the same, then your lines are parallel to one another. So now we knocked this off the list. We got this. Step 1 is done. The median is parallel to both of the bases of the trapezoid. And we know that because if we have 2 non-vertical lines and they're parallel, if and only if their slopes are equal. Okay, so their slopes were equal, so that means then they are parallel lines. 2 lines that are both parallel to the same line are parallel to each other. So I put that one in there in case kind of some books don't really like to have this situation where you have 3 things all parallel to each other. But right, technically you would say that like that this LD is parallel to OP, and LD is also parallel to MN because these both have slopes of 0, and that is a slope of 0. And then you can use that other theorem, that 2 lines that are each parallel to the same line are parallel to each other. So you don't really have to use that if you don't want to. Anyway, LD is C plus D minus A. What am I doing here? What am I doing here? Step 6. Oh, that's right. I'm moving on to distance because I'm trying to figure out like LD, what its length is, because I'm trying to see, is it actually equal to half the sum of these lengths of the bases? Okay, remember these are all generalized it's a generalized trapezoid where we're just assigning variables to figure out the relationships in kind of where this is on the coordinate plane, and then kind of in terms of those variables figuring out distances, because and even though it's generalized, we can still compare them, right? We can still compare them. So LD in the way we've laid it out, and the way that you lay any of these out, you can make an argument that the length of LD is C plus D minus A. Okay, C plus D minus A. So this is in one dimension here because we're not going up or down, we're just going left and right. So the way we can get the distance is the absolute value of the difference. So we can do C plus D minus A, and that would be a positive number because C plus D is over here, which is more positive than A. So C plus D minus A is the length of LD. Okay. That being said, let's go ahead and get the lengths of MN and OP, which are the bases of a trapezoid, which we need to kind of get to. So MN is 2C minus 2A. Okay. So take the bigger X values, back the smaller one. Y values don't change. That's distance formula 2, and OP is just 2D, right? This would definitely be 2D right here, okay? And that's the distance formula. So finally, how are we going to do this? How are we going to prove this, that it has a length equal to half the sum of the length of the bases? Well, this is, we got to add the sum. We got to get the sum of the lengths of the bases, so we'll add those together here, MN plus OP. And I'm actually kind of including this here. So MN plus OP, and here's where I want to go to my pen here. MN plus OP, it's equal to 2C minus 2A plus 2D. MN plus OP gets us to here, and 2C minus 2A plus 2D gets us to here. What's that? What's the reason for that? We can justify that, okay? This is equal to that, and this is equal to that, so we can add the left sides together and add the right sides together, and we would know that equality would result in the resulting equation. That's right. This is the addition property of equality. We take this equation on top here, and we add something, OP, to the left side and 2D to the right side, so we add equal things to both sides of maybe the top equation. We can think of it that way. We get an equal result, and that's the addition property of equality. There's something else going on down here, though, and that is the, what is it? Also the division property of equality, okay? So we, in step 6, we added this to the left side and this to the right side. And since this was equal, we know that the numerators are equal here. But then we also tacked on a denominator of 2. So this is what we're doing, is that I knew we needed to get to this up here, MN plus OP over 2. We need to see what that equaled because we want to make the argument that it's equivalent to LD. So what I did here is, just to save space, I divided both sides by 2, and that is the division property of equality. And dividing both sides by 2, then the 2 gets knocked out here. Yeah, you're saying hi. They can't see you. They'll just hear you in this video. She can stay. It's fine. And then you get this. You get C plus D minus A here. And that's what you got. And where do we see that? We saw that earlier. We saw C plus D minus A. Oh, it equaled LD. Look at that. Look at that. We got them both. We got them both right there. And then we're going to know, right? Because LD equaled this, and MN plus OP over 2 also equal that. We can take them and we can set them equal to each other. That's right, step 6. And here's where it gets messy, and here's where, like, yeah, you know, checking out, doing these math proofs and all, it gets a little messy, but we can get to it. LD is going to have to equal MN plus OP because they equaled the same thing. It's the same thing, as my daughter says. You know, like, she goes and sees the American flag behind our house, and it's in our neighbor's yard, and then we got a flag in front at your grandparents' house we're living at, and she goes, it's the same thing, it's the same thing, they equal the same thing, they equal each other, and there we go. LD equals MN plus OP over 2, and that's for the transitive property, okay? That's it, right? You're going to be doing stuff like this on the homework today, so feel free to get a start on it now. Remember the principles here. Lay out your shape, minimize the amount of unknowns that you have, and then try out that list. We used a lot of this in this here. It comes from that list that I shared with you guys the last lesson of really all of the reasons you're going to need to use on these theorems. They're not much. It's like midpoint formula, slope formula, this thing about parallel slopes being the same quantity, and then perpendicular slopes being opposite reciprocals or multiplying to -1. The distance formula, really, that's about it. That's about it you have there. You're just going to sort of see what follows from it after naming the shapes in an appropriate way. Okie dokie, we got here classroom exercises. It looks like I was planning on going over this with you guys here. So tomorrow, your homework is going to be, you can watch this again tomorrow if you want, but your homework is going to do those C-level problems, which I previewed at the beginning, questions 9 through 13. So the classroom exercises just, we're supposed to go through them because that makes questions 9 through 13, those C-level problems, a little bit more approachable. And the reason why this exists is because we really haven't spent time earlier in the year. I know earlier in the year we talked about the centers of a triangle. And let me write that down right now. Centers of a triangle. Just to remind us, like, what are the centers of a triangle? What were they? Okay. You guys remember? Because there were actually 4. Who's going to tell me? Centers of a triangle. That gives you a hint here. Oh, yes. We had the centroid, which our medians gave us. They gave us a centroid. Remember other ones? Oh, thank you. Thank you for offering that to us. There was the circumcenter. And that was through perpendicular bisectors of each side. The medians of each side were concurrent at the centroid, and the perpendicular bisectors concurrent at the circumcenter. Well, if we're talking about circumcenter, we got to talk about incenter. And that was the point of concurrency by what feature? What feature was in the incenter? That's equidistance from the sides of the triangle. So yeah, we need angle bisectors for those. What's the 4th one? The 4th one, we haven't really done too much about it. Oh, that's right. We got to get altitudes. Altitudes would be that other feature that we'd have 3 of those related to altitudes, related to a triangle. And where did that meet up here? Remember they did that one? That's the one's hard to remember. Well, altitudes are go at a right angle to the side opposite. So this is called the orthocenter. So orthogonal means like at a right angle. The orthodontist tries to get your teeth to go at a right angle with your guns. So orthogonal, the orthocenter, I almost read orthodontist there because I was thinking back to the days when Mr. Fortin had braces. No, he didn't have braces. But his brother used to go to the orthodontist. Oh, yeah. Ha, ha, ha. Sean had to wear braces. Anyway, sorry about that. Braces are cool and all. So anyways, let's go through this one. So we haven't actually proven, right, early in the book, I'm happy this is the way we're going to end because we spent a lot of time on those centers of a triangle, and there are a lot of things you can say about them, but we've never really spent that much time. It's kind of hard, to proving they are concurrent. And what does concurrent mean again? That's a vocabulary word for you. Okay, that is if we introduce all 3 of them, right, all 3 medians, 3 perpendicular bisectors, 3 angle bisectors, and 3 altitudes. So if we introduce 3, would they actually meet in the centroid? If we introduce 3 perpendicular bisectors, would they actually meet at the circumcenter? If we introduce 3 angle bisectors, would they actually meet in the incenter? If we introduce 3 altitudes, would they actually meet in the orthocenter? And that's what you're doing in this assignment right now. So we'll do questions 1 through 8 very briefly, and then I can get you into your homework. Okay, so the purpose of exercises 1 through 8 is to prove that the lines that contain the altitudes of a triangle intersect in a single point. Okay, so this is what we mean by being concurrent. Given triangle ROM with lines J, K, and L containing the altitudes, we choose axes and coordinates as shown. Okay, so through a point outside of a line, exactly 1 perpendicular can be drawn. So we have 1 there through this point, that perpendicular through line MR can be drawn, and then through this point here, this perpendicular, this line J is the perpendicular through OM. Okay, so we're allowed to do that. It's sort of how we start out this proof. Okay, so the way we do this, we chose coordinates like this too, and this is just the reason coordinates is marked is that this is any random triangle. So we know that O is at 0, 0, and then that means R is going to be at A0, and M is going to be at BC. So this altitude here, the key altitude at the beginning to make this our proof of this a lot easier is this altitude K right here. And the equation of this, what type of a line is this, by the way? Okay, so it's going to be perpendicular to the x-axis. That means it's going to be a vertical line. So the equation of line K is going to be x equals b, right? A vertical line has an equation in that format where it has an x-axis, it does an x-intercept, it doesn't have a y-intercept here. So this point right here has got to be b comma 0. B comma 0 right there. Okay, so then this line here is the line x. All the values, x coordinates, are going to be b, and then it doesn't matter what the y values are, right? Just all the y values represented in that equation. Okay, so this is the slope of MR. Okay, so we're talking about MR over here, right? So x equals b is here. That would be the line perpendicular to a line that's horizontal, right? So y equals 0 is the line RO. But anyways, now we're talking about the slope of, we're trying to figure out what the slope of L is here. Slope of L is here. So the slope of MR, we can use the slope formula for MR to get that. This is our delta y here is C, right? C minus 0 over, and then we'd have to do B minus A. Our slope of MR is going to equal C over B minus A. So the slope of line L, this one right here, is if this is our slope of, and I put M here for slope, of MR is C over B minus A, then the perpendicular slope, okay, because line L is perpendicular to MR, so our perpendicular slope is going to be negative 1 over M. Okay, negative 1 over M. So the way to do that is to flip the fraction and make it negative in front, right? So I'll drop a negative in front, and then I'll do a B minus A up top, and over C, right? So that would be the slope of line L. And then if you actually clean that up right here, so I got the same thing here, flipped B minus A, put it to the numerator, put C to the denominator, make it negative. Remember, the slope of the perpendicular line is the opposite reciprocal. And then what I actually did is I moved the negative up top here, which is a legal move, and then I distributed in, made negative B right here, and then negative to negative A is positive, okay? So this here is a cleaner way, right? We're going on the negative in front of writing the slope of L would be A minus B over C. Okay, so that's going to help us a little bit later here. Okay, so the equation of line L is y equals, yes, A minus B over C times by X. Okay, that's the equation. Oh, looks like we put the slope in front of X here. So this looks like this could be arguably slope-intercept form. What is actually, so L, our slope of line L is A minus B over C. Okay, that was because that's the opposite reciprocal of the slope of MR, which we can get through just assigning those variables and using the slope formula. So this is the equation of line L, and we just care about slope, so we just have y equals mx right here, right? And the reason we're allowed to do that is because where's the y-intercept going to be? Oh, it's through the origin. That's right, it's through the origin. That's how it started. Definition of altitude is from the vertex perpendicular to side opposite, and the vertex here, we know we place it at the origin. Okay, so this would be plus 0, and I can explain that here. A minus B over C is the slope from part 2, and then that's the M of y equals mx plus b. And line L passed through the origin, so b equals 0 here. So we don't care. We don't have to write this plus 0 part here. So I'm going to get that out of there. Okay, so step 4. So now we're trying to figure out the common point of intersection. We talked about line K, right? We've talked about line K, and we've talked about line L. We have both their equations. We have x equals b for the equation of line K, and we have y equals a minus b over c times by x for the equation of line L. So using that, we can find the common intersection using a system of equations. We know that x has to equal b, so what we can actually do is take this b and plug it in for x to the other equation to figure out what the y coordinate would be. So here, this coordinate is going to be at b comma something, right? Right here, this is going to be b comma something, where line L and line K intersect. And then later we're going to look at line J to see if it also does intersect these two lines in the same place, or at least just one of those lines in the same place. Then we would know it would intersect both, okay? So this is going to be b comma what? Well, we got to plug in b for x. We do that down here, and then we're going to simplify here. So we're going to distribute b into this. So this is b over 1, right? So our denominator is unchanged. We still have c down here. So b goes to a, and we get ab minus b squared, okay? And so if we're to explain that here, right, k is a vertical line, so we just need to put that x value, whatever x is equal to, we need to plug it into the other equation to find the y coordinate of the point of intersection, okay? So here, this would be b, comma, in our coordinate geometry world, this is AB minus B squared over C would be the Y coordinate. Looks pretty crazy. It is crazy looking. We have to figure out the exact coordinates. Heck no. This is a generic kind of triangle where we're just kind of labeling. We labeled the coordinates and we're seeing what follows. So now that we have this as potentially our coordinate, we're coordinates of the point of intersection of L and K. What are we going to do next? Oh, we're going to see, use the same logic here to see if K intersects J at the y coordinate of AB minus B squared over C. That's what's next, okay? So let's do this. And then we can finally get this proven, that the altitudes have to meet in a single point, okay? Step 5, since the slope of OM, right? So we got to get the equation here, get the equation of J, because then that's going to be easy once we plug in B for its X to see if the y coordinate is the same. Anyways, to get the equation of J, you got to get the slope of OM, which we can do, right? That's C minus 0 over B minus 0. So it's C over B. Look, C over B, we got it here. The slope of line J. So the slope of line J would be the opposite reciprocal, okay? Flippity flip flip. This is C over B. Make it B over C and make it the opposite of that. So negative B over C, okay? Here's the equation of the line, equation of line J. So here, we have a y-intercept that's up here somewhere, but to get the equation of line J, let's see, I explained it up here too. Negative B over C is the slope, and here's where I use something called the point slope form. Okay, so this is, again, I didn't have time to prove this and go through this with you early this year, but this is another way of writing the equation of a line where you don't know the y-intercept necessarily, but you know one of the points. X1, Y1 just means one of the points in the line. So this stands for point slope form, meaning if you know the slope in one point, you can get an equation that represents all the solutions of that line. So J passed this because we do know that A0, look, this line has to go through the vertex of this triangle right here, the vertex opposite this side, in order for this to fit the definition of being an altitude. So A0 is one of the points. We can put in A for our X1 and 0 for our y1, and this would simplify to y equals negative b over c, x minus a. Okay, next step, step 7, is to plug in b for our x here, right? We take that in from step 1. We knew that x equaled b for the line, right? This is the equation, x equals b. So we know that, again, this here is going to be b0, and the common intersection right here between line J and line K is going to have an x-coordinate of b, because all of the x values in this line, x equals b, have the x-coordinate b. So the question is, once we plug in b to this equation for J, do we get the same y-coordinate? Do we get it put in here? Okay, so we're going to replace x with b, and we do that down here, and we're going to simplify this. So we take the slope, and the slope needs to distribute in right now. So we are going to get c in the denominator. That's nice because c is distributing in from a denominator position. And now we just going to do negative b times b, and that's going to be negative b squared. Very nice. And then we get negative b times negative a, and that's positive ab, right? We get a negative times negative, makes a positive, and then b times a. Can't simplify that. We just get ab. And check it out. Do we get the same thing that we got on the other side? Check it out here. Oh, look. Okay, so looking at this here, part 4, this was the y value, ab minus b squared over c. Was it the same here? Yes, it was. Yes, it was the same thing. So the 3 altitudes intersect in a point, name the coordinates. There it is, right there. Okay, so step 4, by the end of step 4, you realize that line L and line K intersected in this world here, the way we've named our variables, at the point b, comma, ab minus b squared over c, and then later you notice that line J intersected line K at b, comma, ab minus b squared over c, and that's the same point. Okay, so that means that all 3 lines go through that point. That means that's where all 3 lines intersect. 2 lines intersect in a single point, so they're not intersecting any other points. They're concurrent in that one and only one point, and we've proven that for altitudes. Okay, so tomorrow night's homework, you're going to prove that for the other centers, so that we have that proven, and hooray, we feel pat ourselves in the back. So you're going to follow logic kind of like this to get there. Okie dokie, here's your homework. You got your Thursday night problem set, numbers, classroom exercises number 1 through 8 all. I just put that on there just in case you didn't watch this video. I want you to struggle with it because I want you to be able to do the homework tomorrow night. So anyways, just get the answers down there. Make sure you understood this. Email me if you have any questions. And then you're also doing the first 8 proofs. So it is 8 proofs. Spend like 5 minutes per problem. I don't know. Don't spend too long on this. Right, you're just getting practice at this point in the year. And then your Friday night problem set, as we get looking close to ending the year, closing out the year. It's just the final 5 problems from this section, and then you can pat yourselves in the back, and hopefully you feel like you have a pretty good grip on what pure coordinate geometry is. Not enough time really to review it all together, and I wish we spent more time on the equation stuff, but I think at least you've kind of seen a complete picture, at least seen what it kind of looks like, maybe not mastered it, and you got to learn to be okay with that because you're in a great position. You guys are going to do great, for sure. All right, take care, guys. Good luck on your homework, and I'm done here. We're done lecturing. Hooray, we've watched all the videos. Have you? Have you really? I don't know, but I haven't done recording them. So Fortin out. I will see you guys later.